Hi, for today's lesson, we'll be learning about homogeneous second-order differential equations. A homogeneous second-order differential equation is a differential equation that has a second derivative as the highest derivative and the equation is equal to 0. For our first example, we have d squared y over dt squared plus 4dy over dt plus 3y equal to 0. This can be written as y double prime, these tick marks are prime, so this is the second derivative, y double prime, plus 4y prime plus 3y equal to 0. So this is a homogeneous second order differential equation because it is equal to 0 and our highest derivative power is 2. In order to evaluate this second order differential equation, we need to take advantage of the property of e raised to some power. So y is equal to e to the rt. Well, its derivative is r e to the rt, and y double prime is equal to r squared e to the rt. So now we can plug these values in for these values. So y double prime, we take r squared e to the rt plus 4 times y prime, which is r e to the rt, plus 3y, which is 3e to the rt. We find that they all share e to the rt, and this comes out. This is often known as the characteristic equation, just the powers of what e could be. So r squared plus 4 plus 3 is equal to 0. The quadratic formula will also work, or we could just see that 1 plus 3 makes 4, so r plus 1 times r plus 3 is equal to 0. We find that we get two powers. R is equal to -1 and r is equal to -3. Now, it is important to remember what r is. So we go back to what our y was originally. Y was equal to e raised to the rt. So our first one is y1 is equal to e to the minus t. And then our second y2 is equal to e to the minus 3t. Now, please notice that we actually got, right here, we got two y solutions. And this is a second order homogeneous differential equation. So this should work. Our general solution is the combination of these two. So y of t is equal to c1 e to the minus t plus c2 e to the minus 3t. These c1 and c2 will change based upon initial conditions. And now some instructors may ask for end behavior. So all end behavior is evaluating the limit as y of t approaches infinity, as t approaches infinity. And then we find, because these are both raised to negative t, that these terms both go to 0. So this implies that this differential equation solution will go to 0. For our second example, we have d squared y over dt squared plus 6 dy over dt plus 8y equal to 0. However, unlike this example, we have initial conditions. Y prime of 0 is equal to 0, and y of 0 is equal to 1. Because this is a second order differential equation, we need two initial conditions. Now, rewriting it in this form, we have y double prime plus 6y prime plus 8y is equal to 0. So now, same as our previous example, we're going to let y equal to e to the rt, y prime is equal to re to the rt, and y double prime is equal to r squared e to the rt. Now, these derivatives were found using the chain rule in calculus. So now we plug these values in back to this differential equation. So we get r squared e to the rt plus 6r e to the rt plus 8e to the rt is equal to 0. We find that they both have e to the rt, and this cancels out. And then we get our characteristic equation, r squared plus 6r plus 8 equal to 0. And then we get our two terms, r plus 2 times r plus 4 is equal to 0, and we get two r values. Now we have our two solutions, very similar to the previous example. y1 is equal to e to the minus 2t, and y2 is equal to e to the minus 4t. And then we get our general solution, y of t is equal to c1 e to the minus 2t plus c2 e to the minus 4t. However, although we have found this solution, we have not yet used these initial conditions. So now we go back and use the original differential equation. So we see for our first initial condition, y of 0 is equal to 1, we use this y of t. This implies that y of 0 is equal to 1. So our y of t, so 1 right here, is equal to c1 e to the 0 plus c2 equal to 0. This implies that c1 plus c2 is equal to 1. Now, in order to use the next set of initial conditions, we need to take the first derivative of the general solution. So y prime of t is equal to negative 2c1 e to the minus 2t minus 4c2 e to the minus 4t. These derivatives were also found using the chain rule. So now we use the initial conditions. Y prime of 0 is equal to 0. So 0 is equal to negative 2c1 e to the 0 minus 4c2 e to the 0. A number raised to the 0 power is just 1. So we get that c1 plus 2c2 is equal to 0. Now that we have two variables and two equations, we can solve for c1 and c2. So one method of doing this is using Gaussian elimination in matrices. If you have taken algebra, you may be familiar with this technique. So all we do is we take the coefficients of each of these and put them in. So the coefficient for c1 and c2 are both 1, and this is 1. And then the coefficient for this value is 1, and the coefficient for this value is 2, and this is 0. Now, I drew a line here to let you know that these are the values it's equal to. And now we can apply row operations. So now we get 1, 1, 1, and then 0, 1, negative 1 because we subtracted the two rows. And then we multiply this row by negative 1 and add to this row. So now we have 1, 0, 0, 1, 2, negative 1. This implies that c1 is equal to 2 and c2 is equal to negative 1. If you are maybe unfamiliar with this method, you could also use other methods in algebra where you may solve for c1. So for example, c1 is equal to 1 minus c2, and then you would plug it back in here and find c2, and then use that to find c1. So now that we have our c1 and c2, we can find the solution to the IVP. IVP is an abbreviation for initial value problem. This is an initial value problem because we have initial values. So our solution is y of t is equal to 2e to the minus 2t minus e to the minus 4t. And our end behavior is as t approaches infinity, y of t approaches 0. These are both raised to negative t. So these terms both at infinity tend towards 0. So I hope this helped you in understanding second order differential equations, the homogeneous version, and thank you very much for watching.